Dear colleagues, I want to present my report. It's named Structure and Mechanical Properties of Stainless Steel Specimens Made by Additive Method After Pulsed Electron Beam Treatment. This work was performed by the team of authors from the Institute of High Current Electronics, and the work pieces for specimens were manufactured at LLC Tete Company, Loskotovo, Tomsk, Russia. And some words about additive technologies. Today it is difficult to find an area of production where 3D printers are not used. They are used to manufacture parts of aircraft, spacecraft, submarines, tools, prostheses and implants, jewelry, etc. The essence of additive manufacturing is to combine materials layer by layer to create objects from 3D models. This is how they differ from traditional production technologies, which imply mechanical processing, removal of substance from the workpiece. Additive technologies are classified according to the material used. They are liquid, bulk, polymer, metal powder, metal wire. By the method of fixing the construction layer, its thermal effect, irradiation with ultraviolet or visible light binding. And by the method of layer formation, its bed deposition and direct deposition. Bed deposition include selective laser or electron beam sintering or melting of powder, and direct deposition includes surfacing of the wire material and inkjet printing. It's only some part of classification, additive technologies. Schematically, the process of additive manufacturing will be presented by six simple steps. The first is preparation of CAD model, creation of STL file, layering, 3D printing, finishing, and obtaining the end product. And one of the common problems for all types of additive technology, as you know, is the problem of surface finish, the fifth step. Regardless of the material and method of growth. Usually the finishing is made by traditional technologies. It's mechanical treatment or machining, or even mechanical, yes, or chemical etching or chemical etching. We propose alternative method of finishing the surface of such material or such product. It's using of pulsed electron beam treatment. That is what my report will be about. As I said before, the workpieces for specimens were manufactured at Tete Company, at the equipment of Tete Company, and for production it uses the technology of electron beam surfacing of wire material. The scheme of the process you can see at this slide. Also technical specification and of the equipment also presented at this slide. This technology in classification named EBF3, electron beam freeform fabrication, it uses wire as material for synthesizing of the products. And about wire material. Workpieces was made using wire of E.S.E.P. company, grade OK hot rod 308 LC with diameter of 1 millimeters. As said, the site of the manufacturing of wire, this material is austenitic stainless steel, and after workpiece was produced, we cut the specimens using electrospark etching machine. The specimen was in the parallelepiped form with sized presented on this slide. And the surface treated by pulsed electron beam surface is a repeat the side of the workpiece. It was the part of the workpiece side. Yes. Treatment by the pulsed electron beam was performed on the experimental vacuum electron beam installation named Solo, which developed and manufactured and at the Institute of High Current Electronics, and it based on the electron source with plasma cathode. The main parameters of the source presented on this slide, and all parameters can be changed smoothly and independently of each other. Irradiation of the specimen was performed in two modes. The first mode of irradiation, it's a mode which include large pulse duration and pulse energy density and number of pulses. This mode was used for rough polishing of the surface, preliminary rough polishing, and the second mode was used for finishing treatment, and it characterized by smaller pulse duration, energy, and energy in this mode change in limited intervals. So this slide presents the images made, same images of the surface of the initial specimen, and you can see some cracks, droplets on the surface, and the surface is heterogeneous. After treatment in sequential irradiation mode, surface looks like a polycrystalline structure without no cracks, droplets, and it's very homogeneous. Surface elemental composition of the specimens showed before and initial and after electron beam treatment showed that it's almost no changed composition, maybe except some chromium, and close to table values for 308 LC stainless steel taken from the site of the manufacturer of the wire. Also, surface micro hardness not changed too in all modes of treatment. Friction coefficient after treatment by pulsed electron beam decrease in all modes, and wear rate in one mode, this last mode, close to initial value for initial sample. Surface roughness and preliminary polished specimens. To define in which mode of treatment we have the lowest roughness, all samples before treatment were polished to the same initial roughness, this 2.73 initial roughness for all specimens. And the best result was for specimen with subsequent irradiation, mode number 1, number 2, with 20 joule per square centimeter. Then in this mode were irradiated sample with original surface topology, which repeat the side surface of the workpiece. And as this surface looks like a wave, the measurement was in two directions. First, it's longitudinal direction and transverse direction relative to the surfacing plate, or substrate. And these measurements show that roughness decrease in 1.5 times in longitudinal direction and about 2 times in transverse direction. Tensile testing of specimens. For tensile testing, the specimens were cut in the form on dumbbell-shaped plate form with such parameters and was treated in both plate sides. To define anisotropy of mechanical properties, these specimens were cut also in two directions, in longitudinal direction and in transverse direction. The treatment mode also presented on the side. And tensile testing of the specimens showed that in longitudinal direction the tensile stress in all specimens almost not changed like before and after treatment, but tensile strain in longitudinal direction increased after treatment, increased on more than 10% relative to initial specimen. But for transverse direction, it was much more than initial sample in longitudinal direction and not change after electron beam treatment. The fracture surface of the specimens after tensile tests shows that the surface, fracture surface looks like a porous and has some inclusions. Also, you can see the thickness of the modified by pulsed electron beam layer, which is more than 25 micrometers. The method for finishing, in conclusion, the method for finishing the surface of metal products made by sequential electron beam surfacing, which consists of, in modifying the surface with an intense pulsed electron beam, is presented. On the example of 308 LC stainless steel, the result of such processing are demonstrated. The optimal modes of exposure are determined. It is shown that after pulsed electron beam processing, a homogeneous polycrystalline structure without cracks is formed on the surface. Elemental composition, strengths, and tribological properties do not change relative to initial material. The roughness of the surface is reduced up to 1.5 times in longitudinal direction and up to 2 times to the transverse direction. This method of finishing can be used both immediately after the manufacture of the product and after preliminary machining. Thank you for attention.